Okay, thank you very much. Today I want to talk about the interactions between outflows and convection. So it's pretty well established from global simulations that outflows will change the convection pattern. This is a plot from the same Wiltberger et al. 2010 study that I showed you a movie of this morning. This is cross-polar cap potential. The red line is the baseline single fluid run without outflow, and the blue line is with outflow. And you can see a clear reduction in the cross-polar cap potential when the outflow is included. So the question in my mind is, what's the other half of that feedback loop? So if you have heavy ion outflows changing the high latitude convection pattern, how does the high latitude convection pattern then feedback and go to change the heavy ion outflows? And I'm going to focus on outflows coming from the cusp region that are energized by wave-particle interactions. So if you have a narrow region of wave-particle interactions, in quasi-steady state, the outflow that's coming up and out of that region is limited by the plasma access into that region. So plasma can get into that region by upflowing from below, driven by frictional heating and other processes, or by convecting in from the day side. So when you reduce the convection speed, you reduce this flux in, you reduce the frictional heating unless you reduce that flux in, so you'd expect this flux to decrease. However, when you decrease the convection speed, you also increase the amount of time a particle dwells in this heating region, and thus it can acquire more energy as it goes across. So there's possible multiple competing effects going on. So I'm going to investigate this using an ionosphere polar wind model that I've been developing, and this model is still very much under development, so consider everything I show as preliminary results. It goes from 97 to 8,400 kilometers. I'm just using an aligned dipole magnetic grid for the moment, and I'm doing Eulerian transport in a 3D grid. The fluid ionosphere polar wind part of the model is based on the 8-moment equations. It's very similar to the Transcar model, for those of you familiar with that formulation. I'm doing full transport for electrons, H+, He+, and ground state O+, and then photochemistry for a whole host of other ions. I've added to this model a phenomenological treatment of wave-particle interactions. So I've added an extra fluid representing energized O+. And I solve a simplified set of transport equations for that extra fluid that retain just enough terms to include the mirror force lifting term, which of course I need. And I've introduced some ad hoc source terms to represent wave-particle interactions in my specified heating region. This model, of course, needs a bunch of other inputs, so I've implemented a one-way coupling to LFM mix. The Magnetosphere-Ionosphere exchange module is the piece of LFM that does the potential solve and the precipitation patterns and so forth. So I'm just reading those in from output files. My neutrals come from MSIS, and I've assumed zero neutral wind, which means that I'm almost certainly going to be overestimating the frictional heating because I've neglected the fact that the ions should drag the neutrals along behind them. So onto my phenomenological energized O+ transport equations. If you think of this energized fluid as consisting of a collection of particles, all of which have the same parallel and perpendicular velocity, and random gyrophases, then you get a really simplified set of transport equations. But they still retain a number of important properties. So these are in the form of conservation of mass, momentum, and energy. They retain convection, so they are dragged along by the E cross B drift. They interact with a self-consistent electric field, and I include the density and the number flux of these particles in my quasi-neutrality and current continuity conditions, such that my self-consistent and ambipolar electric field responds to the motion of these particles. They're affected by gravity, centrifugal force. This orange term in here is the mirror force lifting term. And then I've added some ad hoc source terms to this. So perpendicular heating would drop in right here. And then what I'm calling upsilon here is an ad hoc permotion rate. It's the rate at which I take particles out of the thermal fluid and put them into my superthermal fluid. And I'm only applying the wave particle heating and this permotion in a designated heating region. Now my heating region looks something like this. I put it on the day side at about centered around 10 degrees co-latitude. And I've extended it down to about 1.3 RE, so 1,900 kilometers in altitude. Under extreme cases, it can certainly go much lower, but I'm trying to be somewhat conservative here. And what I've plotted is the flux of my energized O+ outflow fluid at my upper hemisphere at 8,400 kilometers and in the XZ noon midnight plane. And what you can see is the convection drags this outflow outside of the heating region. So I don't just get it inside where I've applied the WPI, it actually gets pulled back across the polar cap, so the ions are going basically that way. So those are just baseline results. To get an idea of how this model behaves, I want to do some simple test cases. So after some time that the model has settled down into something like a steady state, I'm going to scale the potential pattern by simple functions of time. I'm going to do a slow ramp down over 8 hours, a slow ramp up over 8 hours, and a 2-hour period sine wave. And for each of these tests, I'm going to try scaling the drift everywhere it appears. I'm going to try runs where I don't scale the frictional heating term, so I just leave that constant. And I'm going to try runs where I only scale the frictional heating terms and leave the drifts and so forth constant. So here are my ramp down results. The green line here is just the scaling factor that I applied to the convection pattern just to guide your eye. And this is the hemispheric outflow rate integrated over the upper hemisphere. And you can see that the black lines are the case where I've modified the drift everywhere it is included. As I scale down the convection, the hemispheric outflow scales down with it. But even though the outflow rate and the fluxes are going down, the velocities are actually going up. This is the velocity at the poleward edge of my heating region. And as I scale the convection down, these velocities are getting faster. And that's consistent with the dwell time effect. And that effect almost completely disappears in the case where I only modify the frictional heating and thus I'm not modifying the dwell time. Now, in the case where I only apply the frictional heating, I again see this ramp down as I ramp down the convection, but it's not nearly as much as the case where I included everything. And that means that the access to the heating region from convection in from the day side is also an important effect. So here are the ramp up results. It's kind of a similar story. As I ramp the convection up, the outflow rate increases, and the velocity does the opposite thing because of a dwell time effect. Now, not only are the outflow rates changing, but the spatial extent of the outflow is changing as well. So here's my baseline results again. Here's the end of my ramp down, and here's the end of my ramp up. And you can see that when the convection is slower, the outflow gets dragged less far away from the heating region. When it's faster, it gets dragged much further away from the heating region. This is intuitive that this should happen. But the fact that the outflow is coming out of different places means that it will reach different places further down in the magnetosphere, which is potentially profound as to how these ultimately affect the magnetospheric dynamics. And here are my sine wave tests. So again, it's kind of a similar story. The total outflow rate is positively correlated with the scaling factor, and the velocities are anti-correlated. The thing to note here is there's a 15-minute phase delay, because of course the ionosphere can't respond instantly to all these things. And we know that the convection dynamics should be changing on these types of timescales all the time, so these phase delays are potentially significant. So in summary, my preliminary simple test suggests that the hemispheric outflow rate decreases with decreasing convection and vice versa, and this can be explained by changes in plasma access to the heating region. If you were to just use the strange way DC Poynting flux empirical relationship, you would get basically the same behavior. But what I'm saying is that there's actually more to it than that, because the outflow velocity will increase with decreasing convection because of a dwell time effect. And the outflow velocity will affect where these particles ultimately go out in the magnetosphere. Furthermore, the spatial extent of that outflow region, how far it gets dragged away from the heating region, changes. And that will also change where these particles go out. And there are also time delays in the process. So all of these together tell me that we really need to be working as a community towards two-way coupled models to capture all these outflow, convection, feedback loops and mechanisms. Thank you very much.
Very nice talk. Just one question. When you do this modeling, do you apply different boundary conditions in southern and northern hemisphere, for example? I mean, the magnetic field is different.
So
you have a larger offset between the dipole axis and the rotation axis and so on.
So these are idealized runs for a single pole using an aligned dipole. So it's effectively just the northern hemisphere being simulated. And I've only put it in a aligned dipole magnetic field. Eventually, we're going to need to move to the point where we're running two different instances of the model for two different poles and have different offsets for both of them. But none of that's been considered here.
Has anyone done it?
Alex? I don't know if the Plum has done that. Okay, yeah.
We do both the southern and northern hemisphere, but I don't think that should detract from what you showed. I actually thought this was very nice, but I was wondering if you could talk a little bit more about your ad hoc promotion and heating rates, and now they're ad hoc, but how would you envision going to something more realistic in the future?
This is a great question. So my perpendicular heating rate is taken from Bahram et al. 2004. So they did Monte Carlo simulations and compared it to polar cluster data. So I'm just using their numbers. I think what's used in the USU MacPic is slightly different, and I want to look at how different it is and how much that would change the result. The promotion is a trickier issue. So for me, right now, I have that just set to 10 to the minus 3 everywhere in the heating region and 0 out. And ultimately, I want to come up with a way of tuning that based on observations. The trouble with trying to tune that is that the variability in the outflow rate doesn't just depend on the promotion, it also depends on all kinds of other things. So if I do a baseline run and then tune up the promotion such that I say reproduce fast data, if I then change the convection, it'll detune everything on me because of what I've just talked about.
Sure.
What I'm showing here is that outflow can be modulated even if the wave parameters are constant. And so because everything is correlated with everything, it's actually going to be quite difficult for me to figure out the right way to do this going forward.
Well, Andre, Dave Knutson, and I have observations that directly confirm what you're doing on DE, Freya, and one other, Akabono. So you ought to check with reality at some point to inform the way you go. Are you aware of those papers?
I'm aware of some of them. We should talk and see if I'm not aware of all of them.